We look around at our serene blue world and it feels permanent. But step back into the early days of our solar system and that peace vanishes into the violent reality of planetary formation. Across the 100,000 light-years of the Milky Way, millions of dying stars continuously detonated in supernovae. These massive explosions blasted raw heavy elements, things like carbon, silicon, and iron, out into the freezing dark. But that stardust rarely settles into a quiet, life-giving ocean. Most of that raw planetary material is entirely obliterated, swept up into raging cosmic storms, or swallowed by newly ignited stars. Looking at that chaotic crucible, you have to wonder how our specific rocky planet made it through. How did we dodge the destruction that claimed millions of other would-be worlds? The existence of a habitable planet is not the universe's default setting. To get here, Earth had to survive a statistically improbable gauntlet of cosmic filters. The first major test began roughly 4.5 billion years ago. Around our young sun, loose dust clumped into sand, then gravel, then massive boulders, eventually clashing together to form thousands of miniature planet embryos. Further out from the sun, beyond a boundary called the ice line, temperatures dropped low enough for gases to freeze. In this zone, huge planets rapidly swept up the abundant hydrogen and helium, expanding into massive gas giants. The largest of these was Jupiter. It grew so massive it succumbed to the inner solar system's gravitational pull, spiraling relentlessly toward the sun. As it migrated, Jupiter acted like a cosmic snowplow, violently scattering gas and flinging planetary embryos out into the dark. That rampage looks like a total disaster, but it starved the inner solar system of material. By aggressively clearing away massive dust clouds, Jupiter ensured the surviving rocky worlds stayed relatively small, preventing proto-Earth from ballooning into a crushed, uninhabitable super-Earth. Staying small didn't guarantee survival. A Mars-sized planet named Theia found itself caught on a direct collision course with our young world. Theia slammed into proto-Earth, shearing away a full third of our planet's crust and enveloping both bodies in a thick halo of vaporized, superheated rock. Over a century, that glowing debris field coalesced into a single orbiting companion, the Moon. The proof of this shared violence came when the Apollo missions brought geological evidence back to Earth. When scientists analyzed the lunar samples, they found the rocks contained identical oxygen isotopes to those found on Earth. In astrophysics, isotopes act like blood types, and this perfect match proves the two bodies were forged in the exact same collision. The newly formed Moon exerted a powerful, constant gravitational drag on our planet. That friction slowed Earth's dizzying rotation and locked its wildly wobbling axis into a steady, reliable tilt. Without that impact, Earth's climate would swing violently from boiling to freezing as the planet tumbling through space. Theia's destruction provided the mechanical stability required to give us predictable seasons. Predictable seasons mean little if a planet has no water. Early on, the young sun constantly bombarded the inner system with aggressive flares, packing enough energy to blast water molecules apart and send lightweight hydrogen out into deep space. To see the result of that bombardment, look at Mars. Spacecraft observations show it once held vast rivers and oceans, but without a defense against solar radiation, its water was systematically stripped away, leaving a dry, lifeless rock. Earth survived because the Theia impact blasted away much of our thick, original insulating crust. This allowed the deep iron core to cool rapidly, generating a massive magnetic field that wraps the planet in an invisible shield, deflecting the sun's deadly radiation. The exact collision that nearly destroyed the planet forged the magnetic armor that keeps our oceans from boiling away into the dark. Even with its water secured, Earth faced a severe chemical threat. Early volcanoes pumped millions of tons of carbon dioxide into the atmosphere, threatening to trap the sun's heat in a lethal greenhouse effect. We have a clear picture of what that looks like next door on Venus. High concentrations of CO2 turned the atmosphere into a dense, sulfurous cauldron, with surface temperatures hitting nearly 500 degrees Celsius. To avoid boiling over, Earth needed a way to pull carbon out of the air. The solution came from microscopic marine bacteria that evolved a method to absorb sunlight and convert it into a biological battery called ATP. By turning light into energy, they fueled their own growth and released free oxygen as a byproduct. This kicked off the global carbon cycle. Trillions of tiny planktonic creatures, like radiolarians, began absorbing dissolved CO2 from the oceans to build their bodies. As they were eaten or died, that carbon was dragged up the food chain or buried deep in the ocean floor as limestone. Early biology actively engineered the atmosphere. These organisms functioned as a massive planetary thermostat, locking away excess carbon and stabilizing the global climate. Look at the sheer improbability of this sequence: a migrating gas giant clearing the neighborhood, a catastrophic planetary collision locking the axis and forging a magnetic shield. Microscopic life evolving just in time to diffuse a toxic atmosphere. Earth exists today as a highly complex, fragile engine. Map out the extreme cosmic gauntlet it took to assemble this world, and it becomes clear how singular our planet truly is.